Good morning, students. Something simple and small that you love to do will turn your life into an entirely new path. When you know what your passion is, it will motivate you, inspire you to be successful. Find your passion and embrace it and enjoy doing it. Let's move on to today's lesson, Ionic Equilibrium. You must have studied about acids and bases in your lower classes, and you know that acids are sour to taste, they are corrosive, while bases are bitter to taste and they are slippery and soapy to touch. Acids turn blue litmus into red, whereas bases turn red litmus into blue. And we also know that with phenolphthalein, acids give no color, but bases give a pink color. So this is your basics, but in today's chapter we are going to learn about the different theories of acids and bases. Many scientists have attempted to explain the behavior of acids. Let's see the first one, Arrhenius concept. Seventh-day Arrhenius defined acid as a substance that gives H plus ions in the presence of water and base as a substance that gives OH ions in the presence of water. So according to Arrhenius, he defined an acid as a substance that gives hydrogen ions in water. So I take hydrogen chloride gas, when I dissolve it in water, it gives H plus ions, or we also call it as a proton, and Cl minus ions. This water, we said Arrhenius defined the behavior of acid only in the presence of water. So this water takes up the proton given by the acid and forms what is called as a hydronium ion. So protonated water, water which contains a proton, is called as a hydronium ion. Let's look at the examples of some acids. So I have sulfuric acid. So it dissociates to give me two H plus ions and a sulfate ion. And this is HNO3 is nitric acid. It gives H plus ions and NO3 nitrate ions. According to Arrhenius, a base is defined as a substance which gives hydroxyl ion in water. So I have calcium hydroxide. It dissociates to give me Ca2 plus and hydroxyl ion. OH is called as hydroxyl ion. We have another example of aluminium hydroxide, which ionizes to give you Al3 plus and 3 OH minus ions. We also have NaOH, which gives Na plus ions and OH minus ions. But Arrhenius' theory was not completely accepted. There were some limitations. Arrhenius' theory did not explain the behavior of acids and bases in non-aqueous solutions. Only in the presence of water as a solvent, Arrhenius was able to explain the behavior of acids and bases. When non-aqueous solutions were present, he could not explain it. Second, he could not account for the basicity of ammonia that does not have hydroxyl group. According to Arrhenius, an acid should give H plus and a base should give OH minus. But there were some compounds like CO2, SO2, AlCl3 which did not have a hydrogen ion in them, but still they were acidic in nature. And similarly, amine, pyridine, sodium carbonate do not have OH minus ions, but still they are basic in nature. This could not be explained by Arrhenius. So next, two scientists, Lowry and Bronsted, they brought forward the theory. They said that simply that acid is a substance that donates a proton and a base is a substance that accepts a proton. Let's look at an example. I have an acid here, hydrochloric acid, and in the presence of water, HCl donates a proton to water and water accepts a proton from HCl. So HCl is an acid. Water which accepts the proton here is a base. Let's look at the products. I have hydronium ion and Cl minus ion. Here also hydronium ion can donate a proton to chlorine Cl minus and Cl minus can accept it. So Cl minus is a base. Hydronium ion which gives a proton is an acid. Let's look at another example. So as I said, HCl is a proton donor here and it is an acid. Water which accepts the proton is a base. When I come to the products, hydronium ion which gives a proton is an acid and Cl which accepts a proton is a base. Now let us see the behavior of bases in water. I have ammonia NH3. In the presence of water here, what is happening? H2O is donating a proton to NH3. So here water is the acid. What does Lowry Bronsted say? A substance which donates a proton is an acid. So here water donates a proton to NH3. So water is the acid and NH3 which accepts the proton is the base. When I come to the product side, here ammonium ion donates a proton to OH and therefore ammonium is the acid and OH is the base. Let's try to understand the Lowry Bronsted concept. In generally, Lowry Bronsted theory is represented as acid 1 plus base 2 gives acid 2 plus base 1. So I have hydrochloric acid plus water which gives what? Hydronium ion and Cl minus. So as we already saw, hydrochloric acid donates a proton to water. So HCl is the proton acid and water is a proton acceptor which is the base. In the product side, hydronium ion is a proton donor and Cl is a proton acceptor. So here Lowry Bronsted says that HCl and Cl minus are a conjugate acid base pair. What do you mean by conjugate acid pair? The two pairs, any two substances which differ by a proton are called as conjugate acid base pair. Now when you take HCl and Cl minus, what is the difference there? Only one proton. So they are called as conjugate acid base pair. Now let us take these two, water and hydronium ion. Again here what is different? Only one proton. So these two are called as another conjugate acid base pair. So Cl is called as the conjugate base of the Bronsted acid HCl, or hydronium ion, this water is the conjugate base of hydronium acid, Bronsted acid, hydronium ion. So any two substances which differ by a proton are called as conjugate acid base pair. Let's try to understand this with some more examples. Here I have 4 different cases. The first one, phosphoric acid and NO2. In this case, phosphoric acid donates a proton to NO2. Therefore, that is the acid and this is the base. When I come to the product side, nitrous acid HNO2 donates a proton to H2PO4. So this is the base and this is the acid. So as we saw now, H2PO4 minus is a conjugate base of H3PO4. Now look at the second case. I have Cn minus and HCO3 minus. So carbonic acid is donating a proton to Cn minus. So this is the acid and this is the base. And vice versa on the product side, HCN is going to donate a proton. So that is the acid and this is the base. So any two pairs of substances which differ by a proton are called as conjugate acid base pairs. So again we have HCN with sulfur trioxide and water with hydrofluoric acid. Here as you know, hydrofluoric acid donates a proton to water. So this is the acid and water is the base. So depending on whether the water accepts a proton or donates a proton, water can act as both as an acid and a base. Next we are going to see Lewis concept. It's very simple. Lewis says that an acid is a positive ion or an electron deficient molecule. Therefore, if you give electron, acids will immediately take the electron pair. Lewis base is an anion or a neutral molecule. It has at least one lone pair of electron. That means it can donate electrons. So according to Lewis concept, simply we can say that a substance which donates an electron pair is a base and a substance that accepts an electron pair is an acid. Let's look at this example. I have boron trifluoride and ammonia. We know that boron trifluoride is electron deficient compound. How is an electron deficient compound? Boron is a third group element. It has got 3 electrons. Even after sharing the 3 electrons with 3 fluorine, it has got only 6 pair of electrons. For an atom to be stable, we need what? Octet pair. So boron has got only 6 pairs of 3 pairs of electrons, total is 6, and it needs 2 more electrons to be stable. That is why it is called as electron deficient molecule. Now let's look at ammonia. Ammonia is a 5th group element. There are 5 electrons. So even after sharing 3 of its electrons, it has got 1 pair of electron which is not involved in bonding. Such pair of electron is called as what? Lone pair of electrons. So here BF3 is electron deficient, but ammonia is electron rich nucleophile. So what does it do? We know every covalent bond is made up of what? 2 electrons. Ammonia donates both the electron to BF3 to form a bond. It does not completely give, but it just gives the electron to form a bond. And here we can see a bond is formed. So here actually what is happening? This type of bond is usually called as a coordinate bond. Here ammonia is the donor and BF3 is the acceptor. So according to Lewis concept, a substance which donates the electron is a base and a substance which accepts the electron is an acid. So ammonia is the Lewis base and BF3 is the Lewis acid. Let's try to understand with 2 more examples. I have here ammonia, again ammonia, and a proton. Proton, we know hydrogen has got 1 electron. It has even lost that electron and formed a H+. So here ammonium donates both the electrons to form a bond, and I have ammonium ion. Let's look at another organic example. This is acetone and this is aluminum trichloride. Aluminum trichloride, just like boron trifluoride, is an electron deficient species. Here I have oxygen with 2 lone pairs of electrons. So this is acetone. Now what happens? This oxygen donates 1 of its lone pair of electrons to form a bond. And this bond is called as a coordinate bond. As I told you, acetone is the donor and AlCl3 is the acceptor. Always we draw a bond towards the acceptor. So such a bond is called as a coordinate bond. So we have discussed 3 types of acids and 3 concepts about acids and bases. Now let's see some more examples of Lewis acids and bases. So I have here electron deficient molecules are very efficient Lewis acids. So that means what? Electron rich species which have 1 or more lone pair of electrons are Lewis bases. All metal ions which are positively charged, all the cations are Lewis acids. That means what? All anions are Lewis bases. Molecules that contain polar double bond, due to polarity or charge separation, a positive charge will be there, and such bonds can accept a lone pair of electrons. Therefore, such compounds which have polarity in the double bond can accept electrons and act as what? Lewis acid. Multiple bonds that contain carbon-carbon double or triple bond can donate electrons, because a pi bond is there, they can donate electrons. Molecules in which the central atom can expand, we are going to take a lone pair of electrons, there should be some space to house them. So only when the atom can expand its orbital, it can house the electrons, then it can accept it easily. In that case, transition elements or d block elements, they have vacant d orbitals and therefore they readily accept the electrons and they act as what? Lewis acids. All metal oxides which have lone pair of electrons, we saw just now oxygen has got 2 lone pair of electrons and they can act as bases, Lewis bases. Example, I have carbonium ion, here I have carbon ion. So children, we have seen 3 concepts of acids and bases. Let's revise. Hello friends, shall we discuss the 3 theories of acids and bases? Yes, I will explain Arrhenius theory. According to Arrhenius concept, an acid is a substance that donates a proton and a base is a substance that donates hydroxyl ion.
Correct. I will explain Lowry-Bronsted. According to Lowry-Bronsted theory, an acid donates a proton and a base accepts a proton.
Good. And according to Lewis concept, an acid accepts an electron pair and a base is a substance that donates an electron pair. Now we are going to discuss about strength of acids and bases. What is a strength? We can call them as a strong acid and a strong base, or weak acid and a weak base. What are strong acids and strong bases? Depending upon their ionization. A compound, when it breaks to give ions, it's called as dissociation or ionization. So when I take 10 molecules of nitric acid and dissolve it in water, if it breaks immediately into 10 H plus ions and 10 nitrate ions, then it is said to be a strong acid. So immediately when all the molecules which I take dissociate to give ions, then it is called as a strong acid. So nitric acid is a strong acid because all the 10 molecules immediately they dissociate to give you H plus ions and nitrate ions. But look at this acid. What is this acid? Do you recognize? Acetic acid. Just for you to understand, children, I have taken 10 molecules of acetic acid. Just see here, I get only 3 acetate ions and 3 H plus ions. So out of the 10 molecules, only a fraction of the molecule, only 3 molecules have dissociated to give me the ions. So here all the 10 have dissociated, here only 3 molecules have dissociated. Then that is called as a weak acid. So complete dissociation is called as strong acids and base. When they are partially ionized, they are called as weak. So let us try to derive an expression for ionization constant of an acid. Throughout we have been seeing, I have an acid, usually or generally acid is represented as Ha. When an acid is dissolved in water, it gives a proton. Water accepts the proton and is called as what? Hydronium ion and A minus. For this equilibrium, I am going to derive an expression for dissociation constant. Applying the law of mass action, it says the dissociation constant is equal to product of the active mass of the products divided by the product of active mass of the reactants. Now, so I get what? K is equal to concentration. When I write the molar concentration in square brackets, it's called as active mass. So how do you find out molar concentration? It is given by N by V, where N is the number of moles, V is the volume. So when I write the molar concentration in square brackets, then it is called as active mass. Okay, so here what do I get? Concentration of hydronium ion into concentration of the A minus divided by concentration of acid into the concentration of water. Now in such reactions, usually water is present in large excess, so we can neglect it or we can take it as 1. So what does the expression become now? Now the expression becomes H3O Ka, which is now we are going, because it's particularly acid, I write Ka. So Ka, or the dissociation constant or ionization constant of acid, is given by the expression H3O plus concentration of the hydronium ion into concentration of the A minus divided by concentration of the undissociated acid Ha. If it is a base, then I write Kb. Kb will be equal to what? OH minus ion. So sometimes we may 2 marks or 3 marks problems will be there, children. We are going to learn about this in detail in the consecutive lesson. Now let's actually consider HCl. We just saw HA, now we are going to take HCl as the example. Now we know HCl usually dissociates to give what? H plus, and water accepts it, forming proton or hydronium ion and Cl minus. So instead of HA, I have written what? HCl, and instead of A minus, I have written Ca minus. So Ka, the dissociation constant of an acid, is given by this hydronium ion can also be taken as a concentration of H plus. So hydronium ion into Cl minus divided by the concentration of HCl. Now we are going to see ionization of water. So here I have 2 molecules of water. Here one water donates a proton to the other water molecule. So the one which donates is the acid and one which takes up is the proton. So I get what? Hydronium ion and OH minus. So what do we say? Let's recall Lowry Bronsted here. This water and OH minus are what? Conjugate acid-base pairs. Similarly, this water and hydronium ion are what? Conjugate acid-base pair. Now let us try to derive an expression of dissociation constant for the water molecule for this equilibrium. So what will I get here? Concentration of hydronium ion into concentration of OH minus ion divided by concentration of 2 water molecules. That is what I've written it like this. Now, usually the concentration of pure water is taken to be 1. If I substitute that value in this equation, what does my expression become? It becomes K is equal to product of active mass of hydronium ion and the product of OH minus ion. Since it is water, the dissociation constant K is written as Kw, which is called as ionic product of water. Generally, for pure water at 25 degrees Celsius, the concentration of hydronium ion is 1 into 10 to the power minus 7. Similarly, the concentration of OH minus ion is also equal to what? 1 into 10 to the power minus 7. So therefore, I substitute these two values in the ionic product of water, Kw. What is Kw equal to? Concentration of hydronium ion into concentration of what? OH minus ion. Substituting the values, what do I get? 1 into 10 to the power minus 7 into 1 into 10 to the power minus 7, or Kw is equal to 1 into 10 to the power minus 14. So this value is called as ionic product of water. Since the concentration of hydronium ion and OH minus ion are equal, water is a neutral compound. It is neither acidic nor basic. When this hydrogen ion concentration or OH minus ion concentration vary, we get different acid and basic solutions. So children, we have covered very little bit, but let's see. What did we learn? Arrhenius theory. What did Arrhenius say? An acid is a substance that donates a H plus in the presence of water, base donates OH minus. Next, Lowry Bronsted. They just said proton donor is acid, proton acceptor is base. What did Lewis say? Electron pair donor is base, electron pair acceptor is acid. Then we saw the strength of acids and bases and what is meant by ionic product of water. Children, revise the lesson, take up the Kahoot, but keep revising. Thank you, students. Stay safe and be happy.